In this video and exercise, we look at the graphs of trig functions. Now, some of you will be familiar with these graphs. However, you previously probably drew the graphs where your x-axis measured the angle. However, that was the angles were measured in degrees. We're going to see the same looking graph. However, we need to become familiar with labelling our x-axis in terms of radians. So you will see that here in this example, and the rest of the graphs that are in the notes here. The other important feature of this exercise is to introduce you to some terminology associated with trig graphs. Now, trig graphs, the sine and cos in particular, are what we would call wave graphs. And with all wave graphs, there are particular features. One feature of the wave graph is its amplitude. So it's important that you are familiar with this term and clearly understand how to identify the amplitude for a particular trig graph. So by definition, the amplitude is the maximum height of the wave above the mean position. Now remember, I said these are wave graphs, so they're repeating themselves, they're keeping the same pattern up and down. We would say for this particular one, the x-axis is actually the mean position. It's actually the middle, exactly the middle of the graph. And so the amplitude for this particular graph is the distance that the graph goes above or below the actual middle position. Now, I know that below it's called -1, but we don't label the amplitude as a positive or a negative. Well, we don't label it as a negative. We don't measure it as a negative. We just say it has an amplitude of 1 unit in this case. You'll see amplitudes can change by us introducing a constant into the function, and you'll see that happen a little bit later on. So that's amplitude. The period is another concept that is a feature of trig graphs, and remember I said that they are wave functions and that they repeat themselves. So if I draw one complete cycle, which more correctly is called the period, you can see that it just keeps on repeating that exact same shape. Now, it's the distance over which it repeats itself, and actually it would have been much nicer if, I'm not sure why I can't get that off, if I'd actually started, for example, maybe here and went to here. You can see that that's starting at -2 pi, and when I get to 0 I have completed one period is the correct term. So the period for this particular trig graph is 2 pi. After 2 pi radians it will repeat itself, and actually from here to here is a measure of 2 pi again. It's just not as obvious as the second highlighted section. We also can apply similar rules and techniques regarding translations that we found with previous functions, like our basic graphs, our straight line graphs, the translations of our quadratics, the translations of our cubic, the translation of an exponential, the translation of a log graph. All those techniques that we learned about, whether it be moving the graph to the right or moving it to the left or up and down, all those translations apply to Trig graphs. So we're going to see that working as well. And we can also use the property about even and odd graphs because these trig functions nicely demonstrate evenness or being odd. So there's lots of features of the trig graphs which you have are not really new. Terminology might be new, but features are not that new. And you'll be able to see similarities and differences between the trig graphs. So that first graph is the graph of y is equal to the sine of x, or f of x is sine of x. We can see it has a period 2 pi and it has amplitude 1. It is an odd function, and we can see that the sine of minus x is equal to minus the sine of x. That's the property for a function being odd, and that applies to the sine graph. Like I said, the transformations of previous functions also apply now to trig functions, and I was saying that the amplitude could be altered by introducing a constant at the front. We know that the we don't call it amplitude, but introducing a constant, say, in front of our quadratic, our x squared, we saw that impact on the actual graph. The same with the cubic, or the same with the exponential. We are aware of the impact that adding a constant at the front actually has, and it has a similar impact here with our trig graph, and we measure that. We give that actually a name when it comes to the trig functions and call it the amplitude. You can add a constant on to the whole graph, and that will move the curve up by c units, because I'm used to c here. The negative of the function reflects the curve in the x-axis. We saw that with previous functions. Applying the negative inside directly on the x reflects the graph in the y-axis. We saw impacting directly on the x again by subtracting a constant moves the graph to the right. And just another term, it's a phase shift. Now it's more a science term than a maths term to talk about the phase. And introducing a constant directly on the x is how we impact on the period. We're going to see more on that. Now, remembering that the definition of cosec x is 1 on sine, produces a very interesting graph. We have places anywhere where the sine is actually equal to 0, then we'll clearly have the reciprocal graph undefined, because you can't have 1 over 0, and so we get lots of points of discontinuity and a very interesting graphs produced as a result of taking the reciprocal. Moving on to the cos graph. It's very similar in that it has period 2 pi, it has amplitude 1, but it has this concept called a phase shift. It's been moved. Now, it is the cos graph, and it instead of going through the origin, it starts at when x is 0, the well, the cos of naught is 1. So we've got to start our graph up here. But you can see that, yes, it has a complete period of 2 pi, from 0 to 2 pi, and it's back to where it started. You know, the best thing you can do is to, yes, look at these graphs and register the features of them, but it's much more important that you actually draw them. If you get stuck on drawing any, use Wolfram Alpha, use any sort of graphing program you're aware of. If you're familiar with GeoGebra, then use that, or like you commonly see me use Wolfram Alpha, you can use that one as well. But please always graph. Don't leave any graph or any graph anywhere in any of the topics unsketched. You could always go to a graphing program to get you some help as to where you're going with your graph. And I would always strongly advise you to do that rather than just leave it and not have an understanding of the graph. The more graphs you see, the better you'll become at it, and the more graphs that you force yourself to sit down and draw, again, the better you'll become at it. You have to be very proficient at drawing graphs, mostly because in trigonometry, you often just get asked to draw the sketch of the graph, and as well as that, you know that for you to work out the calculus, especially with regards integration and finding area, you need to be able to draw a graph. The cos graph is a nice even graph. Looking at the reciprocal one on cos, again we'll have lots of points of discontinuity, because anywhere that cos is 0, which is at all of these points here, the reciprocal graph will be undefined, and it looks like this. The tan graph, I think most of you are familiar with. It has lots of points of discontinuity. It's an odd function. It has an amplitude of infinity, and it has a period of pi. It has asymptotes as a feature of the tan graph. And again, it is odd. And the reciprocal function is called cot, and it's quite similar to the tan graph. There's some summary points there, and we'll come back to these aspects of impacting on the period, impacting on the amplitude, etc. But for now, the most important thing you can do is to draw the graphs. Practice drawing the actual graphs. You'll see that your graphs support lots of properties that you've previously come across. You saw that for obtuse angles, the sine of x plus 2 pi, now that's actually moving into the reflex angle, or the angle in the third quadrant is equal to the sine of the acute angle. You can actually see this happening on your graphs. Here we've got our obtuse. The sine of 2 pi minus an acute angle is minus the sine of pi. Now that's a property you would have learnt when we looked at the trig in the unit circle, and you can actually see it happening now on the graphs. You should be right to do exercise 4C.